Okay, so it's a great pleasure that we finally have Juan Soler here. Juan is an expert on ISM physics, star formation, and he is also close to the magnetic field. His heart is in the right place. We share this common interest, right, of the magnetic field. So a few words about Juan. He got his PhD from the University of Toronto in Canada, working on blast-ball. And then he has moved everywhere in Europe, pretty much, starting with Paris, where he worked on Planck, and then went to Germany, Heidelberg. Then he was for some time in Italy. Now he's in Vienna. He has worked both on observations and theory. He has many significant contributions to the field. He's known for several things. One of them we talked about today, but there are others that especially that have to do with the direction of the magnetic field and its dynamical importance, right, in the different phases of the interstellar medium. So Juan, you have the floor.
Thanks, José, and thank you all for being here. So while I remove this from here, well, let me first thank you. Whoever has worked in magnetic fields note of the Crete School of Magnetic Field Studies. So I have collaborated with Gina Panopoulo, Aris Tritsis, Rafael Scalidi. So it's a pleasure to me to know that not only my heart is in the good place, but also like my interest in the magnetic field is in the best place to discuss. So I know you are not all magnetic fields lovers or H1 lovers or even galaxy lovers. Too bad because we live in the galaxy. But I'll try to make a summary and like an old band play some of the classics. I'll talk a little bit about the magnetic field, and then I'll talk about the neutral atomic hydrogen emission, H1, that you may know. So many things have changed. So the first one is now I'm no longer in Rome. Now I'm in Vienna. I'm leading my own group, and I'll be talking about magnetic fields. So on top of H1, there's magnetic fields. And before we start, let me thank my collaborators. Part of this big team, the EcoGal collaboration in particular, the PIs are the people in the first row there. Okay, so why are we talking today and why is this interesting? So the key problem is the baryon cycle in the Milky Way, how the diffuse gas condenses to form new stars and how those stars come back into the interstellar medium. The material in those stars come back into this interstellar medium. There are several important phase transitions there. One that goes from the atomic gas into molecular gas that cools more efficiently and enables that gas to cool down and eventually form new stars. When the most massive of those stars enter into the main sequence, they release energy in the forms of winds and radiation. And when they die, they release material and energy and momentum in the form of supernova. That creates this cycle over here. So this is very nicely schematically, but we have problems understanding how fast this happens, what are the key physical ingredients in this cycle. And in particular, I'm going to be talking about three questions today. The first one is how fast is the gas becoming available for star formation? How fast that diffuse gas condenses? How the star forming regions interact with their environment? Are they isolated or they're connected? And last but not least, how the molecular gas is dissipated and goes back into the ISM to repeat the circle. If you see these are how questions, that means that they're not easy because they describe a lot of description of many physical processes across scales. So I'm going to give you a view of the two aspects of this big problem. The ISM is too big for just one astronomer. So I just specialize in two parts of that. And it's acknowledging that all of these processes happening in a magnetized medium and that the diffuse gas is a very important part in understanding that. I'll be talking about H1, neutral atomic hydrogen, that composes around 60% of the gas in the Milky Way. And I'll be talking about the magnetic fields. Okay, so with that, this is my menu. I hope I'll be talking a little bit about magnetic fields. So let me time. So I don't want to be in a rush and we're kind of in a small audience, no? So I'm going to be talking for 45 minutes, as initially stated. And let's see how we get there. If you have any burning questions, if you have any controversial question, maybe you save it for later, so we don't have a discussion in the middle. But if you have any questions, any clarification, please let me know, and I'll be happy to go over that. Okay, so let's start. All right, so why magnetic fields? Well, magnetic fields are very interesting because they're everywhere. They are permeating our galaxy. This is a picture from 2000. This is the magnetic field that is observed with starlight polarization. You can see that this is not homogeneously sampled. People like places where stars are formed. They're mostly interesting. And now we have increased that number of stars by almost a factor of 6. So we have around 60,000 stars that reveal this pattern of magnetic fields. Magnetic fields are cool because they transmit force into the matter through the Lorentz force into ionized medium, and that ionized medium is coupled to the neutrals through collisions. So even if you're neutral, a small amount of ions is enough to couple you with magnetic field. So you're not completely independent from the Lorentz force. You can observe a starlight polarization, but in a starlight polarization, unless you can observe in the infrared, you're limited to the places where you see stars in the background and where that starlight can actually transmit. So an alternative way of doing these observations, particularly towards star-forming regions that are very dense, so you don't see stars in the background, is using submillimeter polarization. So you think of a star for which the intrinsic polarization is none, so the oscillation plane of the electric field can be any. If it goes through through a magnetized medium where there's dust grains that introduce a preferential direction in the polarization of that light. So you measure blue starlight polarization, because those dust grains get warm again, tens of Kelvin, so they emit light in the submillimeter. So you can observe the submillimeter polarization to observe the orientation of the magnetic fields in places where the starlight polarization doesn't go through. That has a big problem, and is one, most of that submillimeter light doesn't make it to the surface of the Earth. The atmosphere is optically thick to those wavelengths, so you have to measure it with a balloon or with a satellite. And that's what I was doing for a number of years. We flew this mission, BLASTPOL, that Costas was nicely introducing, and this is a very traumatic experience. It's so traumatic that I wrote a book about it. So I'm happy that there's another Spanish speaking in the audience. So maybe you can check my book about my trauma. So this is BLASTPOL. This is one of the ships that got trapped in Antarctica during the heroic age of exploration. I'm not saying that it was as traumatic as going to Antarctica back in the day when you only had wind to propel your ships. So it's pretty damn traumatic. So we don't talk about that. What happens when your experiment doesn't work and you have no data and you have been 5 years into your PhD? You make data. So you ask your simulator, trusted simulator, in this case was Patrick and Abel, and we wanted to see how would these clouds that we're going to observe with BLASTPOL would look if the experiment worked perfectly. And they look like that. And of course, in a simulation, you can try different flavors of magnetization. So on the left-hand side, you see a weak magnetic field. So quantified by beta. So this means that the turbulent pressure is a factor of 100 higher than the magnetic pressure. And then you have a strong magnetic field where the magnetic pressure is a factor of 10 higher than the turbulent pressure. And you can see by eye that these images are not the same. So the idea was not only to describe, because these are fake molecular clouds. These are 4 by 4 parsec parcels of gas, isothermal. So who cares what story you make about that? Maybe you care about like the story of Chameleon or Mosca or something like that because they're real clouds. But these clouds, you cannot describe them in the same way that we are used to describe our observations. You need something that allows you to not only compare them, but compare them to other simulations and to the real observations. So what did we devise to systematically compare these things? Well, there's one thing that comes across, and is, yeah, the field seems to be more regular here than here, but also the coupling between the field and the matter. So here in colors, you see the column density for this molecular cloud, and in the drapery pattern, you see the orientation of the magnetic field. And it can come across that actually the orientation is a bit different in the two simulations. So we wanted to quantify that, and the way we decided to quantify it was using, yes.
Periodic boundary condition?
Yes, periodic boundary conditions. So this is an infinite molecular cloud with a mean temperature of 11.4 Kelvin, so isothermal, and initial density such that it would collapse. So for sure, this thing would collapse. So a way in which you can describe a scalar field, as is the density field, is through its gradient. So you can transform a scalar field into a vector field that then you can compare with the magnetic field. And you can quantify the angle between those two vectors, between the gradient and the magnetic field, to see what is happening across densities. And that is what we did. So in that particular experiment, what we saw is in the weak magnetic field case, the orientation of the field and the density structures is almost always parallel. So for the density ranges that we had in the simulation, magnetic fields are always parallel to the density structures. When the magnetic field is strong enough, you have a transition. Initially, you're mostly parallel to the magnetic field, and for the highest density regions, you're perpendicular. And this is in this perfect experiment, and we could synthesize everything of those results here. So we have 2 time steps, those would be the 2 color curves, and then we have 3 flavors of simulation: weak magnetic field, intermediate magnetic field, and a strong magnetic field. Strong with respect to what? To turbulence. And what we saw is that if the magnetic field is not dynamically important, you never have that transition from mostly parallel to mostly perpendicular. This is in 3D. So when was the data available to actually do this comparison? With Planck. Planck was a satellite of the European Space Agency that flew between 2009 and 2013, and it wanted to do something very weird that is called cosmology. And they wanted to measure something very strange, that is the polarization of the CMB background and of the cosmic microwave background emission. Why? Because they wanted to understand B modes and some other exotic things, tensor to scalar modes, so things. I was in the cleaning department. I was supposed to clean that signal from them, but that signal is actually very nice, is what you see here. So this is a picture of the emission that Planck observed at 353 gigahertz. So here in colors, you see the amount of dust along the line of sight. You can see the inner galaxy, you see the outer galaxy, you see some nearby regions, and in the drapery pattern that is made with a technique called line integral convolution, what you see is the magnetic field orientation projected in the plane of the sky and integrated along the line of sight. This was the largest number of polarization vectors registered in the submillimeter ever made. So this is the data that you needed to actually study the field inside of those star-forming regions. And we took 10 of them. Why these ones? Because I didn't know anything about molecular clouds in the day. Remember, I was doing instrumentation. They told me that these were important. So there are more. But what is very clear is that we had to pick them at high galactic latitude. Because if you pick towards the galactic plane, your line of sight depth is very deep. And at 353 gigahertz, most of the, along most of line of sights, you have no, they don't get optical effect. So you're seeing really through the whole galaxy. So if you go to higher galactic latitude, you can avoid that integration problem. And then you have pretty pictures like this. So for these 10 clouds, all of them located within 500 parsecs from us, what we found when we compared the relative orientation between the column density contours and the magnetic field is that we had this trend. So you go from mostly parallel, from mostly perpendicular with increasing column density. So what is this number that I'm showing you here? This is a weird number. Juan, what are you talking about? What I did is I turned a problem of relative orientations, a problems of angles, into a random walk. So you can experience it today. You go and drink a few rakia or a few uso, then you go out and then you experience a random walk. And you can assume that each one of the polarization angles and gradient vectors that you measure corresponds to a walk in the complex plane. So in the weird complex plane, remember that in polarization, you only measure orientation, you don't measure direction. So this is the same as this. So this complex plane completes one loop after you're at 180 degrees, okay? If you take one step to be each one of the angles that you measure in the map, a preferential orientation would show as a direction in this random walk. If all of the steps are in the parallel direction, you would move a lot in this axis. So your projection is going to be very long in that axis. If you're perpendicular, you would be very oriented in this direction of the plane. And if you're random, and if you drink a lot, this is what you're going to find. You don't go very far from your initial point. That's why this statistic is called the projected Rayleigh statistic. Why is it no? Why should you know about this? Because this is a sigma when you have a circular distribution. So a sigma, a Gaussian distribution, is ill-defined when you wrap your field, because if you make a very broad signal, then it's going to wrap on the other side. So sigmas are bad in the angle space. This is a sigma. So when I show the relative orientations for the magnetic field orientation, when I say 15, I'm saying 15 sigma for a preferential orientation parallel magnetic field and density structure, and the same for the negative. So this is the poster child of that. This is the torus molecular cloud. So we have a very high significance of the result, and we go from mostly parallel to mostly perpendicular around 510 to the 21 particles per square centimeter. So column densities where you start getting a little bit above of AB of 1. So in that case, we see this transition. This is the transition that we had predicted for a relatively strong magnetic field. It's very hard to calibrate magnetic field strengths from this crossing because, as you see, this is not a linear relation. And it's also very affected by the orientation of the magnetic field. So it's very hard to infer the magnetic field strength, but we know that we wouldn't have this if the magnetic field was not dynamically important. So we have that transition, and that transition has some significance because people have seen it before. So this is for the projected Rayleigh statistic, funky thing that this guy is talking about. This is for the same for angles. So you go see, you go from 0 degrees to 90 degrees. And you see that the error bars saturate. That's because actually when you measure error bars of angles, sigma is not a good description of that statistic. Okay, anyway, so we're here, mostly parallel to mostly perpendicular at around 21.7 particles per square centimeter. And that's kind of familiar if you work in the magnetic field, because something else happens there. That's when you go from a magnetic field that seems to be bound on the upper level. So these are observations from Seyman, the Seyman effect. That is the only way that we have of actually measuring the strength of the magnetic field. So that's when things start to scale from mostly flat around here in H1 and OH, when you go into the dense core traced by the cyanide radical, and it starts going up. The slope of this relation is controversial. Costas has some thoughts about that. I have some thoughts about that too. Everybody has thoughts about that. You know why the error bars are like this? So some people say that it's because of the orientation of the magnetic field. But the secret is these are the tears of the astronomers that suffer producing the Seyman observations, because this is a very, very hard observation to make. You have to measure circular polarization, you have to control your systematics very well. So this is a very painful measurement to make. But we know that there's something changing at around 10 to the 21, 510 to the 21 particles per square centimeter. So we know that we have this transition in the orientation angle, and then we have the scaling of the magnetic field. You can have different interpretations about this. One of the interpretations is the one that we made. I'm going to show you the cartoon version. We explain it in terms of the transport equations of the magnetohydrodynamics in this reference. So if you're into equations, you should go to that one. But basically what is happening is when you're in the diffuse medium, the Lorentz force dominates the flows. So you have to follow the magnetic field lines, and motions perpendicular to the field lines are quenched by the Lorentz force. So you can only accumulate matter parallel to the field lines. And once you start gathering material, the material gathers perpendicular to the magnetic field. And in this direction is balanced by the thermal pressure. So that is the only way in which you can accumulate material in a magnetized medium until you accumulate enough mass such that you can beat the magnetic field, or once you lose enough ionization that you can have dissipative phenomena like ambipolar diffusion, for example. So that is the cartoon. In this paper, we show that this is related. This transition happens when you have converging flows, when you have a negative divergence of the velocity. So this is our version. Some other people have other versions. So has it ever happened to you that you read a paper and then you're like, I should have wrote that paper, it's so good. Well, that happened to me. So fellow Colombian Juan Ibáñez Mejía, Mordecai McClure, Ralph Klesen did the same analysis, not in terms of the transport equations of MHD, but in terms of the forces. So if you're a test particle living in different densities in the ISM, what is the dominant force that is acting on you? So they did it for, this is a simulated molecular cloud. These are generic initial conditions. So they took a box, 1 kiloparsec box, shake, of course, stratified, because in 1 kiloparsec you have the galactic plane. And they check, and then they pick some clouds there. This is just an example of one of those clouds. All of these relations have a strong variance across time and depending on the cloud that you pick, but the relation is more or less the same. So let's say you're a particle and then you're at 10 to the minus 1 particles per cubic centimeter. These are the three forces that you would experience. One, pressure. So you have a gradient of the pressure. So you would this would be an inward force. You would have Lorentz force, so a current cross B, and then you have gravity. As you go into denser and denser medium, you start being, so in the diffuse medium, you're dominated by pressure and by the magnetic field. So that is what I said before. But as you go into the denser and denser medium, one thing is going to happen, and is that first the H1, the neutral atomic hydrogen, is going to cool down. So you lose thermal pressure, and you're going to start forming molecules. So even you're going to lose temperature. So here, the thermal pressure is going to go down. And what happens is that you're going to accumulate mass more effectively. And there's a threshold in which actually the gravity, the self-gravity of that lump of material is going to be the magnetic field. So I think that where we're seeing this transition between mostly parallel and mostly perpendicular is this sweet spot. When you're actually dominated by the magnetic field, thermal pressure doesn't do much, and then you cross at a point where you accumulate enough matter such that the magnetic field lines get pinched, and then you have the change in relative orientation. So then I had a dichotomy, no? With Planck, we observed a very sweet spot in column densities and also with a very coarse resolution. Planck was a cosmology experiment. So we measure everything at 5 arc-minutes resolution. That is 0.2 parsecs for nearby clouds. So where can you go from there? You can either go into the more dense medium or into the more diffuse medium. That was the crossroads in which I found myself. So if you go in this direction, you need another experiment. You need more resolution to look inside of those star-forming clouds. That's what we did. So BLASTPOL eventually worked. So it's not so dramatic. It eventually worked. We make this map. This is a beautiful map with multiple orientations. And what we found with BLASTPOL is that this trend, the mostly parallel to mostly perpendicular, is not extended to higher column densities. So we found some parts of that cloud that indeed go from mostly parallel to mostly perpendicular beyond the limit of Planck. So this dashed line is the limit of column densities that we had with Planck, because resolution in the end is also a column density limit. But some others, they just go back up to random orientations. So this is not something that is continuous all the way in. And if you remember, because it's a balance between gravity and magnetic forces, it is possible that in some pockets of material, magnetic field beats the gravity, and in some others, the gravity is beating the magnetic field. So there is a balance there, and that is confirmed by observations. This is from Hawk Plus. This is from Sofia. This is a particular region that is hidden there, but it is a Serpent South region. And Tushar Pillai saw beyond the limit of Planck, and then she saw that the apparent alignment, so parallel to perpendicular, will look like this. And then Tushar Pillai saw that you have kind of a loss of alignment. Actually, things tend to be parallel when she sees inside of these clouds at high resolution. So it becomes a mess, and it does become a mess. So when you follow up Planck with Nika2, the polarimeter at the 30 meters in Iran, you see the same trend that we observed with Planck in a more distant cloud. So this is another hidden cloud. This is G75, so mostly perpendicular in the dense regions at around the same scale as Planck. But when you zoom in using an interferometer, that orientation kind of becomes random. It's very hard to predict the orientation of the densest stuff from the large scale magnetic field. Kind of decouples as we expect. Some places magnetic field wins, some others gravity wins.
Protostars inside your densest region?
In this one, no. This one is prestellar. It's a prestellar clump. It's a high mass prestellar clump. And we know that it's not just one, actually it's two, but that's a separate issue. Okay. But now in the other direction, that takes me to the second part of my talk, and is what happens in this region. So I'm not going to talk more about that, what happened in the diffuse region. What you see in the diffuse region is the interaction between the diffuse material and maybe the flows that form molecular clouds, or at least what is going on in the diffuse medium. So here you can see a summary of everything that we talked about in the first part of the talk. So you see torus is mostly perpendicular, Orion mostly perpendicular, Orion B mostly perpendicular, and in the diffuse medium, you see how it threads around the diffuse medium. Here's the galactic plane, so here's a mess. But in this object, this is the Orion-Eridano superbubble. This is one of the largest superbubbles because it's very nearby. This is at 250 parsecs more or less, and this is like this big in the sky. It's gigantic. And this is the medium that is around the most nearby clouds. Taurus is here in the front, 140. Orion A is at 450 parsecs, and the Orion-Eridano superbubble is kind of here in the middle. So that is the part that called my attention. What is the H1 doing? And how is it following the magnetic fields or something else? As you can see, this is not only the magnetic field, there's a big cavity here. So that is what I'm going to talk about in the second part of the talk. So far, so good? Okay. Brace yourself because now begins the H1 part. Okay. When you talk about a star formation, usually people associate the idea of star formation directly with molecular gas because it seems to be a prerequisite for that. We know that that is not the case. You can have cold gas, and also the first stars maybe didn't form in a completely molecular environment. So this is a panorama of the most nearby star formation regions. So you have familiar names, Orion A, Carina Nebula, Chameleon. These are observations in the carbon monoxide emission. So people tend to think of star-forming clouds as islands, archipelagos of very dense material. But there's a context to all of them. So actually, if you look at this map in another color, this is emission measured by Planck in carbon monoxide. If you switch the light and you look at the H1 is everywhere. And it's actually connecting all of these regions that look like archipelagos. So it's a little bit like if you see Crete and you imagine that Crete is an island in the universe when actually it's connected to everything else underneath the sea. So you need to see beyond to see where is the connection between these islands of star formation and the rest of the ISM. Can I have a show of hands? Have you guys ever seen the galactic plane of the Milky Way in H1 emission? Okay, great. So we have the majority. So now let's put some velocity in this. So this is what you see in the H1 when you go across velocity channels, okay? It's a beautiful mess. People have seen different things at different stages. You see some bubbles, some people see very big loops. There's some obscuration, so it's a very big mess. So what you're seeing there is the emission from the hyperfan transition in the hydrogen atom, the most simple atom of them. You have a proton and you have an electron, and you're seeing the transition of the spin. You're seeing the switch between the spin. This is my favorite topic at the moment because it's actually a very beautiful story. The H1 line was predicted during the Second War in the Netherlands, in occupied Netherlands. Jan Oort had to go to Leiden to teach classes hidden to Van der Horst, to Hendrik van der Horst that did the prediction. Hendrik van der Horst thought that this was never going to be possible to measure, that this was hopeless. Josif Szkłodowski independently in the Soviet Union derived this and actually found that it was three orders of magnitude more likely that we could measure that. He went to observe a solar eclipse in Brazil, and he mimeographed translated copies of his paper, because remember, it was very hard to leave the Soviet Union. Those copies of his paper made it to the United States, where the Americans thought that the Soviet Union was about to measure H1 for the first time. And that motivated Edwin Purcell, that, by the way, is the inventor of magnetic resonance. He was the first one to prove that you can have magnetic resonance in solids. That's why he won the Nobel Prize 2 years after he discovered the H1 line. And his student, Ewan Purcell, who could have all of these papers translated, including Van der Horst's paper that was originally written in Dutch, because he was working for the Navy in the radar system. So when he came back from the radar system, they mounted an antenna in Harvard, and they couldn't measure the 21-centimeter lines, but there was a weird visitor. Edwin van der Horst was visiting Harvard at the same time that they were making this observation, and told them, guys, if you measure the difference between channels in H1, you're doomed, because actually the H1 line is very broad, so you have to start switching between more distant channels. So he helped them measure that. Then they told the secret to Jan Oort of how to tune the receiver so they could measure also from the Netherlands. And at the same time, Philip Kerr was visiting from Australia. So the line, the 21-centimeter line, was measured simultaneously, almost simultaneously, in the United States, in the Netherlands, and in Australia in 1951. all within the interval of 3 months or so, mainly because of coordination. So it's a beautiful story, but probably you don't want to hear about that. What you want to hear about that is that we know now that actually H1 is most of the diffuse gas that is out there. And it's important because this is the gas reservoir from which you're going to produce these condensed clouds in which you form stars, but it's also where you receive a lot of the energy and momentum that you produce with the most massive stars. So this is the first image of the distribution of H1 lines. So in this axis, you have galactic longitude, and in this direction, you have velocity, so the Doppler effect of the line. And what you're seeing here is basically the galaxy rotating. So when you see it towards the galactic center, positive, negative, negative, positive, this is the pattern of us being off the center in a rotating disk in H1, and you can assume that you can map all of these motions into distances if you expect that everything is going around the galactic center. Okay, this is what we call kinematic distances. So you go from the line emission that gives you position, position, velocity into something that is position, position, distance, assuming that everything is moving around the galactic center. You can assume the rotation curve, and then you can have a face-on view of the galactic plane. This is the first face-on view of the galactic plane. This is Kerr, the guy that was visiting Harvard when the H1 line was measured for the first time. He was working in radio emission from the moon. And then he saw the observation, and then he said, I want to really do this. And then he led the observations of H1 from Australia. Jan Oort, led the observations from the north. And Westerhout was a grad student when this was being done. So this is the combination of two hemispheres from Australia and from the Netherlands. And this is the first face-on view of the Milky Way. It was not the last one. This is a very coarse beam. So actually, if I may remove that bar, okay. The resolution of this map was 2 degrees. If you tell that to an optical astronomer, he would laugh in your face. 2 degrees is gigantic, it's bigger than the moon. But the observations have improved. So this is already at 30 arc minutes, and this is already at 15 arc minutes resolution, and with different methods. The center part is always tricky when you try to do a face-on view of the Milky Way. Because when you do the solutions for where the material would be, given its radial motion, you have an ambiguity. It can be in 2 places. It can be nearby or far away, if you assume circular rotation. So most of the people vacate that region. There's a second complication, and is that the orbits are not completely circular around the galactic center. We have a bar, and that bar has its own motion, and it's complicated to model. Some people are very brave, and they have made observations like this, and it seems we're converging. Like you see some features outside here that look like this one outside like this one, and then the inside remains controversial. But we're at 2025. That is true. He's not, probably in 2025, he was in high school. Okay, and let me get rid of this bar because it's kind of in the way. Okay. Yeah, 2025. So this is the latest stuff. This is people that I work with, Baso, and hopefully are going to do a better reconstruction. I'm not into this parallel arc business. Sorry, it's my bias. What am I on? Global properties. So one of the first things that that was noticed in these face-on distributions of the Milky Way is that the galaxy is not flat; it's actually warped. So in one side, it goes as high as 6 kiloparsecs over the mean plane, and in the other side goes a little bit beyond 2 kiloparsecs. So it's slanted. So it's the form as a potato chip. So next time you have potato chips, think that this is how the Milky Way looks. What else do we know? Okay, so this is a reconstruction from from my work at 16 arc minutes resolution. What else do we know? That not only the Milky Way is warped, it's also flaring. So it's opening. So this will be like the moment 2 of the vertical distribution of the gas. So the Milky Way bent like a potato chip, but now the potato chip is opening on the sides. Most likely this is because of the potential. Most of the stars are in the center, and the potential starts getting weaker, and then it connects to the higher galactic latitude medium. This is the same reconstruction. The amplitude of this flaring is from around 500 parsecs around the solar neighborhood to almost 3 kiloparsecs in the outskirts. So the flaring is a lot, and it's also asymmetric. What else am I into? I'm into bubbles. Not into measuring the bubbles, but just bubbles are beautiful. So you already saw this image. And I'm not the only person fascinated by that. This is an image made by Carl Heiles. This is from one of the first surveys. This is made with the Hat Creek telescope, close in Northern California. And Carl made this image in the same way that the first color photography was made. He took 3 projectors, he projected 3 velocity channels, and he put filters, cellophane filters in front of that, and then he took a picture of this in the wall of his house. His wife is an artist, so that really helped. The whole here is the part that cannot be covered from the Northern Hemisphere, and then he noticed the same thing that you guys are noticing. We're machines of making patterns. This is the Orion Aridana super bubble, and Carl saw that everywhere. So he saw bubbles. And he was not the only one. People have been looking for bubbles, so things that are semicircular. And then the smoking gun for a bubble is that in the center, you should see 2 components. You see the front and you see the back. And people have been looking for that. And then in the middle, towards the edges, you should see only 1 component. People have been using that principle to look for shells and supershells by eye. This is the work of Sonia Lerova and Jean Palouche. They were really measuring. Sometimes they went crazy, no? I mean, but some others are bona fide bubbles. So bubbles are cool. Bubbles are nice. Actually, they seem to have a profile with respect to the Milky Way. So now what you're seeing in the x-axis is galactocentric radius. Each vertical lines correspond to one of the bubbles in those catalogs. And this is compared to the latest profile of star formation of the Milky Way that we produced with David Elliott. So you can see that first, there's a clear change in the star formation. You have an almost 2 orders of magnitude change between galactocentric radius of 5 and galactocentric radius of 10. Well, a little bit more than 10. You really have less star formation. We know that that is also the case with the population of high mass stars. As you go further and further out, you have less high mass stars. So you expect that you have less progenitors of these bubbles. And indeed, you see less bubbles as you go out. Can be biased because, well, identifying bubbles is difficult. If you're further away, it can be even more difficult. But there's another way of sampling this. This is the same image of the H1 survey. But here, what Carl Heiles did was apply a filtering into the H1 emission. So this thing that looks like a worm can be turned into this series of filaments. So he's just band passing this image. And then he found these vertical structures that he called chimneys or worms. Worms because they seem to be crawling out of the galactic. So this is with the old data, and what Carl proposed as an origin for those structures is that most likely these are supernova that happen too close to the scale height of the disk. So they explode in a pressurized medium, and as they expand, they reach a medium that is less pressurized. The wall opens and produces this vertical structure. So that is what I wanted to measure. So now I'm going to show you. It even has music. So this is a bit of the multiple observations of H1 in the galactic plane. And what I did is I tried to describe this mathematically as filaments. So now we're going backwards and seeing velocity channels, and is a description of the same field, but now in terms of elongated structures, of high aspect ratio structures. I'm going to let you guess what is the width of those filaments. Is the beam. We are not resolving this structure. So actually width is not a very interesting feature. Also, these structures, you see how they collide, and also this is in velocity space. So good luck measuring length, because most likely these things are not even co-spatial. So length is also not a good thing, or at least it's not a thing that I like. What is very well defined is their orientation. So that is what I want to measure. So the way I produce those maps is with the Hessian matrix algorithm. So you take a second order derivative, then you trace what is the direction of the maximum change. With the eigenvectors, you can make a map like this one. So you transform a map of intensity of H1 into a map of filaments. What you see in the gray background is because this was an interferometric image. So we wanted to make sure that we're not just seeing the crap from the patterns from the interferometer. And then you can make a map of angles. But I know how to deal with a map of angles because I work in the magnetic field. So you can turn everything into a spectrum of angles. So I already told you that the angles are not good. I can use the projected Rayleigh statistic. So I go from a spectrum of intensity that looks like this toward a spectrum of orientations. So for example, for this style, for this 1 degree portion, actually 2 degree portion of the galactic plane, I have the intensity, but I also have the orientation. So for this, I have a 10 sigma, mostly parallel to the galactic plane, and just a few regions where it's almost perpendicular, but it's mostly undecided. So for this particular example, actually the H1 is mostly parallel to the galactic plane. What happens when you take the whole galactic plane and then you decompose it like this? This is what happens. So now, again, this is the x-axis galactic longitude, but in this case, I'm not showing you intensity in the colors, I'm showing you orientation. So what I find is that most of the stuff is red, which corresponds to mostly parallel to the galactic plane, and there's some selected regions where you're mostly perpendicular. If you fold this in using our assumption of circular rotation around the galactic center, you see that most of the red stuff is happening in the outer galaxy. It's not exclusively happening in the outer galaxy. You have some outer galaxy stuff that is also blue, but it's definitely changing with galactocentric radius. So in another representation, you can put it like this. Red, mostly parallel, blue, mostly perpendicular. You have a profile of changes in the anisotropy of the H1 emission as characterized by these filaments. These filaments, for most of the cases, describe almost 80% of the flux in H1. So you have that they're like this in the inner Milky Way, and as you go into the outer Milky Way, they start getting flatter. So we know that that's how the bubbles behave, but that's also how the star formation profile behaves. So as you're in the inner galaxy, most likely you have more sources of those chimneys that lift the material very efficiently. And as you go outside in the galaxy, beyond the solar circle, you have less supernova. Each supernova has to cover a larger volume, and then you have a less effective impulse in the vertical direction. This is how it looks in a map. So towards the inner galaxy, you see lots of features going up and down. And towards the outer galaxy, it gets a little bit flatter. So how am I doing time-wise? Good. Okay. So now we have simulations actually to test this. This is a kiloparsec box, a 500 parsec box. It's a tall box, so in the vertical direction, it's 2 kiloparsecs. And we're going to see what happens when you turn on supernova in an stratified medium. So you see the bubbles pop, as Carl Hayes rightly found. You have some hot gas that gets released into higher altitudes, and you have the molecular material that stays close to the plane, but actually the vertical structures remain. So I think what we're seeing is the remain of those supernova explosions that accumulate multiple of those vertical chimneys. How about the magnetic field? We tried with the magnetic field. The magnetic field is not strong enough to keep stuff in the disk, but it's strong enough to keep it coherent. So you quench fragmentation. When you have higher magnetic fields, you still have the chimneys, but those chimneys fragment less. So actually you have more wispy filaments in the vertical direction. When you have a galactic simulation, you can see that the shear motion produces some elongated filaments in the outskirts of the galaxy, like here. And random supernova don't do the trick. If you just take random supernova, they barely influence the galactic potential. This is a synthetic observation from Rowan Smith simulations. And what we see is if you randomly place a supernova, they don't produce this effect. You have to really have clusters of supernova, accumulated supernova, to produce this effect of feedback that lifts material very efficiently up and down from the plane. So I'm going to go a bit quicker. We saw that we're not resolving the filaments. Actually, if you see at 4 times the resolution, the effect is there, but the orientation remains the same. So these are the bands that are covered by GALPHA. So actually red becomes even more red. The filaments that have this horizontal preferential orientation actually resolve into smaller structures that preserve some of that orientation. And the same happens when you go even a factor of 10 in resolution. So we go from GALPHA now into Thor, the highest resolution survey of H1 towards the galactic plane. And then you see that these guys just don't resolve into random structures. They resolve and they preserve some of that orientation. So I'm going to go fast over this one so I can arrive to this. Okay. What happens to the rest of the gas? So this is the H1. The H1, remember, mostly perpendicular in the inner galaxy, and as you go to the outer galaxy, it flattens out. The CO doesn't behave like that. The denser gas does not remember this motion. This is something that is happening to the diffuse gas, actually in the CO. So this is the CO observations at comparable resolutions. The CO is mostly red. The CO in the inner galaxy is mostly parallel to the galactic plane. As the H1 forms its chimneys, the CO remains in the galactic plane. You can see here, this is the galactocentric profile. As you go into the outer galaxy, the CO doesn't have any orientation. The preferential orientation is random. But in the inner galaxy, it's very significantly parallel to the galactic plane. Here are the comparisons in some other metrics. You can go to high resolution and you get the same. Okay, now to finish, I'm just going to show you an alternative to just assuming circular motions around the galactic center. So remember, all of this scheme that I was showing you was based on the assumption of circular motions around the galactic center. That is an assumption, but we know that that is not the only thing that is happening. You saw the bubbles. The bubbles produce motions back and forth that are different to just circular rotation around the galactic center. So what can we do about that? Well, there's an alternative now, and it's the fact that we have reconstructions of the 3D distribution of extinction in the interstellar medium. Those reconstructions are usually limited by extinction, by the number of stars that you have, but you can do very good reconstructions like this one. So this is one of my favorites. This is the work of Gordon Engelhofer. And this is the galactic plane constrained to B plus or minus 5 degrees. And then you can see some of your favorites, the Radcliffe wave, the split. These are all local features. So what you gain with this is that you can anchor the H1 structures that until now you only knew how they were moving. You can anchor them into positions in space. How did I anchor them? I use morphological matching. I just look at them. If they look alike, that process can be painful, but we know how to do it thanks to Google. So when you Google an image, effectively what it does is compare the edges of that image. And that is exactly what I did. So if you want to, these two images have something in common. I'm not going to tell you what it is. You can describe them effectively using the gradients. So old trick that you know from magnetic fields, and then you have the gradients. The intensity of the gradients is not very informative, but the orientations of the gradients are quite unique. So if you compare the orientations of those gradients, you can know exactly whether those images match. You can see that we found the object that was in the two images, and then we have some spurious correlation. Actually, it's a spurious correlation that Google knows very well about, because all of the images taken by humans, or most of the images taken by humans, have a particular anisotropy. Can you guys guess what it is? The horizon. All of the images, we always know that up and down. So this is what you're seeing. This pink splur that is there is just because this is an image that was taken on the Earth. Okay, so we can do the same and quantify that with the projected Rayleigh statistic. So I did it for the galactic plane. In the galactic plane, I split the galactic plane in 10 by 10 degree tiles, and I made the reconstruction. So this is an example of how to match shapes. This is blind. This is the highest correlation that I found. So this thing and this thing and this almost doesn't have CO. This is a very big H1 cloud. It's actually relatively close to us at 176 parsecs. And you can do the same experiment with CO. And here is the reason why you cannot do this just by painting the CO or the H1 with extinction, is because the H1 is not always positively correlated with extinction. Sometimes you can have high extinction that looks like a decrease in emission in H1. This is not because you're decreasing the amount of H1. This is because you're seeing the coldest phase of the H1 on top of a very warm background. So this is tricky because we don't know to begin with where those regions of decrease in emission are. So here is an example that kinematic distance don't always work very well. So this is for a particular tile. Actually, this is the tile towards the Radcliffe wave, surprisingly enough. This is the CO, and these red lines are the expected result of kinematic distances. So the CO actually is well within the kinematic distance. So in this axis, you have distance, so the slices of dust that you get from the 3D dust reconstruction, and in this axis, you get the velocity. So what you're seeing here is that actually the CO is moving very well with galactic rotation, but the H1 is not. You have big excursions, you have up to 20 kilometers per second offsets with respect to what you expect from the circular motions around the galactic center. And that is expected. If you have a supernova explosion, the gas that is dense is going to be less affected, but the H1 is just going to be blown around. And that causes large offset motions with respect to galactic rotation. You can quantify that here. So this is the reconstruction that I have for the motion of the H1 and the CO. H1, CO, red, blue, red, blue. This is what you expect because we're rotating around the galactic center. So this is the expectation from one rotation curve. So you can subtract that motion and then you get something like this. So you see there's no large scale pattern in this rotation. I'm going to give myself one more minute. And then you have the drift, the amplitude of the drift motion. So for H1, we have that on average, the RMS of that offset with respect to galactic rotation is around 11 kilometers per second. That is the average value that you'll be wrong if you assume that you're moving with circular motions around the galactic center. And it's less for CO, we know, because it's more dense, most likely it's moving. And what we calculated from that was a kinetic energy. Why kinetic energy? Because nobody had measured an actual kinetic energy. So I went to Bruce Drain's book. This is the Bruce Drain book on, this is the first chapter. This is like page 5 in stellar medium. And in his book, he gives some measurements of the energy density. So we know that more or less they're around 1 electron volt per cubic centimeter. And the only one that had not been measured actually was this one. He estimated that out of the mean density and some average velocity dispersion or some even lower, but this was not measured. This is the first measurement of that number. So this is this 0.11 electron volts per cubic centimeter. This is an estimate of the kinetic energy in the local ISM. You can multiply by 3 if you believe in equipartition, because this is only for line of sight motions. But we know from what I showed you before that there's an anisotropy. The vertical motions are not the same as the horizontal motions. So you have to be careful. But even then, you can do an estimate of how much energy, how many supernovas, what is the source for that energy density that you get. If you assume some energy density from the supernova, you assume a conversion of the thermal energy from the supernova into kinetic energy, you get that you need around 1,500 supernova to get that number. You know how many we have with the most current studies of the ISM, clustering and reconstructing the population of clusters that we observe now? We have 400. We're missing at least a factor of 4 in supernova. And this is integrated over the last 30 million years. If you multiply this by 3, then the density set is even larger. It's almost more than 1 order of magnitude. So somehow supernova don't do the trick by themselves. We have this energy that we have to explain. Either there's some large scale motions that are cascading down, but supernova don't do the trick. It's not just a medium that is dominated by the supernova. And I'm going to leave my summary there. And thank you.
Thank you.
Launch star winds before they go.
The problem of the winds, we're seeing that in the simulations, because so the amount of energy that you put with supernova is around the same amount that you get with the winds, so 10 to the 51, but the winds are integrated over the life of the star. So it really depends where the star is. So it's really hard to model, but it doesn't do the trick. Like that would add you like a factor of 2, but not more.
What about arcades gonna be?
Oh, good question.
Sorry, I had a follow-up question to that. So you mentioned that the estimate is 400 supernovae in the last 30 mega years, if I understood right.
Yes.
Now, we know from radio observations that there are about 300 something supernovae observed now, supernova remnants observed. And the lifetime of the supernova remnants is not more than 50,000 years, 100,000 years in the radio. So we know that in the past, about 100,000 years, there were of the order of 300 supernovae. So I believe that this number is grossly underestimated.
Mm-hmm. It could
grossly, be. I mean, we're talking like we observe, we know that there are about 300 supernovae in the past 100,000 years.
But over the whole galaxy.
Years. In the radio covers a large fraction of the galaxy because it's almost expired. And this is about 30 mega years. I mean, it's 300 times longer time scale.
But this is for just the local kiloparsec. So this is for the same volume that I studied.
Oh.
Exactly.
Right.
It's because it's the local volume. Sorry, I should have put.
How large is the hole?
In the clusters, they go to 1.5, 1.2 kiloparsecs.
All right.
So it's much smaller.
Okay.
It's much smaller.
Okay.
Yeah, sorry, I should have clarified that.
Okay.
Parking stability. Well, we tried. I mean, that was kind of the beginning of that. But when we made this, these maps of orientation, that is part of the reason why we put the arms, try to see if there was any correlation. But the truth is, it's very hard to pinpoint specific places, and especially if it's very deep into the inner galaxy. So, for example, here, I don't know if you can see me online, but if you go into the positive velocities, for example, in the first quadrant, the magnetic field that you see with Planck, for example, is just the integrated signal. And if you go further, for example, with infrared observations like Dan Clemens did, you go up to 2 kiloparsecs. So you're actually not going to the places where you see the big changes. So yeah, parking instability is there. We just interpreted everything in terms of supernova, but as I showed myself in the end, maybe not everything is supernova, but it is hard because of this integration effect. And to know that it's parking instability, you would really need to measure the magnetic field, not only the H1
But the relative weight is very ordered and it's a huge structure.
I have thoughts about the Radcliffe wave. I don't think it's as long as Joao thinks. I think in each one you really see it interrupted by Orion, but I mean that's my personal view. So it could be. Actually, now that you mention it, I'm going to use that question as a trap because we found something interesting too. So this is a map that we produced with Thor. So remember, all red. This is mostly parallel to the galactic plane. Thor by design was measuring around B of 0. So unintentionally, we observed a part of the galaxy where the galaxy was going up. So we didn't see the galaxy, we see something else. That is this object here. So there, the galactic plane is actually up here. And then we found this guy. This guy actually traces almost to a few velocity channels. It's on the other side of the galaxy. So we get it with kinematic distances, but also making kind of a ladder of distances. We call it Magdalena. I'm Colombian, and Magdalena is the largest river in Colombia. So I wanted to pay homage to my country. You can see that it's mainly cold. You can see that the spine is diffuse. And this is 1.7 kiloparsecs long. It's oscillating. Blue, red. And this is atomic. It doesn't have any CO. So we do know that there's structures like that, but this one is 500 parsecs below the plane. So if that is parking instability or not is tricky. But beyond the Radcliffe wave, which I mean, this is a long discussion that we have with Joao every time we talk, so it's okay. But we know that these oscillating structures may be out there in the galactic plane. I don't know if they're always.
Is this visible from the north?
Yes, this is visible for the north. Yeah.
So, and how far away is it?
17 kiloparsecs.
17 from
Yes.
us.
Yes, it's on the other side of the galaxy.
Oh.
So it's obscured. Or although maybe, I don't know, we would have to check. No, it's obscure. I mean, you see it there in Gaia. So it's really beyond that. It's kind of at the edge of that dust. We could check. We follow up with Parks, not with Parks, with well, we follow up with Effelsberg to see if there has any OH. Sometimes it has OH, but for sure what it doesn't have is CO. We don't see it in CO. So this is an atomic filament. It has 10 to the 5 solar masses. It's below the galactic plane. So if you have any ideas for how can such a thing be there, they're more than welcome.
Any other questions? No? Okay, let's thank Juan again.